Today, we're going to wrap up the last bit of material I need to review with you all. This integration. So we're going to be refreshing your memory on integration. Again, a lot of these images and screenshots and formulas were pulled from old notes. So if you have those, it's good to have them out. This is more so, like I said, to refresh your memory of what we covered at the beginning of this year. When we first started talking about integration, that was the reverse of derivatives, and it also dealt with essentially when you're given the derivative, now you're looking for the original function, okay? It also represented how to find the area underneath a curve and the x-axis, and one way to do that through approximation or through estimates was using the trapezoidal rule. This formula is in your reference booklet, and so you just need to know essentially what each of the variables represent and then how to use it. So H is the formula of B minus A over N. That is not in your reference booklet. You have to know that H represents B minus A over N, where A and B represent the boundaries of the area that you're trying to approximate. Okay, so A and B, they represent the boundaries, the upper and lower boundaries. And N represented your number of trapezoids, okay, or your number of sections that they wanted you to approximate the area to, okay? And of course, Y represented your function. So, of course, this is the formula. There is a way to do it by hand, but I also showed you guys how to do it in your calculator. Because in your calculator essentially gets you your Y1, your Y2. You can still use your calculator and still get your method points when you're doing your approximations or your estimates. So we're going to do this example here. It says estimate Y equals -3, X minus 2 times X minus 8 using 5 trapezoids on the interval from 2 to 8. Okay. So knowing that, you know that A is going to be 2 and B is going to be 8. And so, and then also that N is going to be 5 because that is the number of trapezoids that they want you to estimate the area for. So to find H, you would just do 8 minus 2 divided by 5, which is 6 over 5, okay? You needed that because in order to do what you need to do in your calculator to get your Y0, Yn, Y1, Y2, and so on and so forth, you needed that H. So to do this, we went to Stat and we went to Edit, okay? And here is where we essentially put in a few formulas to help us in finding out the Y part. So in Y1 is where we essentially would represent each of the boundaries of those trapezoids that we're trying to create to get this estimate. Since we have 5 trapezoids, we always started at 0 and we went all the way up to the number of trapezoids that we had. So in L1, you essentially are putting your number of trapezoids starting at 0. Always start at 0. Then in L2, we actually went to the title for L2. And in L2, this is where we put X sub I. Now, if you recall, X sub I represented A plus, was it HI? Yeah, it was HI, yep. H times I. Now, I essentially represented what we already have in L1. And so we just had to take our values of L1, multiply them by H, and then add our A. Yes, our actual A from the interval. That's what went in L2. So A is 2 plus H, which we found to be 6 over 5. And then we're going to multiply that to our I's, which are sitting in L1. So second 1. And then by doing this, the calculator does the work for us and comes up with essentially the different locations for where these trapezoids are going to be underneath this respective curve from 2 to 8. Then in L3, that's where we actually put the function to make sure that we populated our Y0, our Y1, our Y2, and so on and so forth. Okay, so in L3, this is where we actually put the function, but we put it with respect to L2. In other words, instead of us typing in X for our function, we're typing in, we're going to let the calculator basically input in each of the L2 values. So in L3, we would go up, make sure L3 is highlighted, and then we continue to type in our function, which is -3 x minus 2. But instead of putting x, we will put the actual x values from the L2 column, then subtract from 2, and repeat the same process for x minus 8. But again, by using L2, the calculator is going to find essentially the area of each of the trapezoids in those respective intervals. So when we click enter, there it is populated. That is our Y0, our Y1, our Y2, our Y3, our Y4, and our Y5. That's going to go into our formula to estimate the area. This is how you use the trapezoidal rule. So for this particular problem, we'll have 1/2, and this is what you would actually write on your test if you were asked to estimate the area. 1/2, we know that h is 6/5. Y sub 0 is the result from L3 when it was 0, so that's 0. And Y sub n is essentially Y sub 5, because remember we're using 5 trapezoids, so then that would be this value here of 0. Then we'll have 2 plus Y1, Y2, essentially everything in between our starting value of 0 and our ending value of 5. So that'd be plus 2 times 17.28 plus 25.92 plus 25.92 plus 17.8. This is actually what you would write on your paper with the formula to get all your method points as well as your accuracy points. So type that in and tell me what you get. So we essentially type that in and we get 103.68, which does round to 3 significant figures of 104. And that would be the estimate for the area underneath the curve from 2 to 8 of this particular function. It's an estimate, okay? That's what trapezoidal rule provides. It provides an estimate of the area. That came first before the more exact way to actually find the area underneath the curve. So we'll revisit this, the same example, when we get to that part in the review. A good question was asked. If it doesn't specify to use the trapezoidal rule or like the rectangular method or the other ways, how do we know? Well, one thing is that if it says estimate the area, then they're wanting you to use not the calculator, not the fundamental theorem of calculus. They want an actual estimate. You'll always default to trapezoidal rule because that is what you guys need to know for this class. And even if it doesn't tell you the number of trapezoids to use, like in this particular problem does, there will be something else given to you. There may be a table that's divided into sections, and then that will be the number of trapezoids that you would use. So good question. How we went about actually finding the exact area came from us using this rule here to find the antiderivative of a function. The antiderivative of a function helps us find the area of a curve on a particular interval. But this is where we started. This is the baby step way to get up to that point. Essentially, if you have a power function, to find the antiderivative, you added 1 to your exponent and then divided by that new exponent. And of course, you put your plus c. You cannot forget your plus c. It's worked for power functions. That's all the types of functions that you guys deal with. So different from derivatives, where you would bring down the exponent and subtract 1. The antiderivatives where you add 1 and then divide the coefficient by the new exponent. So if you're asked to find the antiderivative of f prime of x equals negative x squared plus 8x minus 12, it's essentially asking you, okay, what's the original function? So you take the antiderivative of each piece of that function. So each term you would take the antiderivative of. So you add 1 to your exponent and then divide by your new exponent. So what's 2 plus 1? So this becomes negative x to the third over 3. What about here? What's the exponent on this x right here?
1.
So 1. So then you add 1 to that exponent, that becomes 2. So this becomes 8x squared all over 2. And then this one doesn't have a variable. So how do I do the antiderivative of a constant? That's the derivative.
12x.
It becomes 12x. Because technically, this is 12x to the 0 power. That's what causes there not to be a variable at all. So then you add 1, and then that's how you end up with x. Then you would have your plus c. Of course, you want to simplify from this point. X to the third over 3 is the same thing as saying 1/3 x to the third. 8 divided by 2 is 4x squared minus 12x plus c. And this is how we use the antiderivative to help us find the original function. Now, of course, you should never forget your plus c. That c represents a constant, because realize there's several functions, there's infinitely many functions that have this as its derivative, okay? How you find a particular equation, if there was another piece of information, let's say that there was a point on the graph at 0, 1. Then in order to actually find the value of c, you would plug in that point for x and y, because this is equal to f of x, and then you would solve for c to get your function, okay? So if it actually asked you to find the original function and you were provided with additional information like the value of x or a particular point, you would plug that in for x and y, solve for c to get your actual function. Like so. You would find out that c would be equal to 1, because clearly all these other terms cancel out. So then your full function, if 0, 1 were a point on the function, it would be negative 1/3 x to the third plus 4x squared minus 12x plus 1. And then that would be your final answer. But if it does not give you any additional information, you provide the plus c, and the orange would be where you stop. The last little bit of integration dealt with the fundamental theorem of calculus, which is how you actually found the area underneath the curve. This too is in your reference booklet. And essentially what it means is that from one bound to another bound of a particular function, you would find the antiderivative, plug in your upper bound, and subtract it from when you plug in your lower bound. Okay? Here's an example. The integral from 0 to 6 of negative x squared over 6 times x minus 6 dx is asking you to find the area of this curve from 0 to 6. Algebraically, I will want to distribute to have negative x to the third over 6 plus x squared dx, I would take the antiderivative, which means I add 1 to the exponent and then divide by my new exponent. What's 3 plus 1? 4. When I divide by 4, there's already 6 down there. What do I do to the 4 and the 6? If I have 1/6, x to the 3rd, and this becomes 1/6, x to the 4th over 4, what do I do to the 6 and the 4? I multiply them. So it turns into what?
1 over 24.
24. What's the antiderivative of x to the 2nd?
X over 2 or x over 3.
It would be x cubed over 3. Make sure you keep that exponent there. So then what you would do is you would evaluate it from 0 to 6. You would plug in your upper bound into the function. For all of your x's. Then you would subtract it from what you get when you plug in your lower bound. Luckily, our lower bound is just 0. So 0 over anything becomes what? 0. So that whole part is gone. So then you're left with negative 6 to the 4th over 24 plus 6 to the 3rd over 3 that you would type in and get your answer. So our area would be 18. That'll be the area underneath the curve from 0 to 6. Now, granted, this is the algebraic way. This is how you can show that the area is 18. In your calculator, there was another way to do this. By pressing the math button and going down to option 9. Going down to option 9. That allowed you to actually have an integral that you would fill in all of your information. 0 to 6. Your actual function of negative x squared over 6. Again, I got there by pressing math 9. And then don't forget your dx. Essentially, whatever the integral is, you just type it into your calculator exactly how you see it. Click enter, and we also get 18. That is how you do it using the calculator. This is how you do it algebraically. Yes.
To get the method points, would you recommend to use a calculator or the fundamental theorem?
Calculator is not going to get you the method points, and depending on what directions went with a problem like this, that is how you would do it algebraically. Actually finding the antiderivative and then plugging in your upper and lower bound. If you can get to this point right here of finding the antiderivative and plugging everything in correctly, you'll get your method points for sure. Then you can use your calculator to just get the answer. Really and truly. So refreshing your memory on that, going back to the estimate for this particular function with the 5 trapezoids, let's see how far is the estimate from the actual exact area underneath the curve. I'm going to do this using my calculator. So what buttons do I press?
Math 9.
Math 9. What's my lower bound?
0.
Careful.
Oh, wait, no, that's 2.
2. And my upper bound is?
8.
8. What do I put here?
Don't you put that equation?
I put the equation, I put the function. Here I can just leave it as x's. I don't have to, do no L1 or L2 because I am using the calculator to get my exact area. Make sure I put that x on dx and click enter. It's called an estimate for a reason. The exact area though is 108. What if the question asked me to find the percentage error? What if the question asked me to find the percentage error of the estimate and the exact?
Don't you have to do the estimated value minus the actual over the actual?
Yes, there is a formula that's in your reference booklet under prior knowledge called percentage error. You take the estimate, you subtract it from the exact and divide it by the exact. Take the absolute value and multiply it by 100, and that will give you your percentage error. So essentially, how far off were you by using the estimate? Where do I find the absolute value bars in my calculator? Who remembers?
Wait, what was the question?
Where do you find the absolute value bars in the calculator?
Oh, that I don't know.
It's all right, because what does the absolute value do to a number?
Make it positive.
It makes it positive. So if you did this, you just did 104 minus 108 divided by 108, you know that should be a positive number. So then you just, when you write your answer, it'll just be a positive 3.70 for your percentage error. Absolute value bars are located under math and number, ABS. So math, number, ABS. Figure I use that time to review another older concept I don't think I've talked about in our reviews, but that can still be a question that's asked of you is in your prior knowledge. But it's essentially integration, the trapezoidal rule with your estimates, antiderivative, how you actually find a function, using that to apply to the fundamental theorem of calculus, which is how you find your exact area underneath the curve and between the curve and the x-axis. So let's take a look at this one. It says the equation of the curve is y equals negative x to the third plus 4x squared plus x minus 4. A section of the curve is shown in the diagram below with the 3 x-intercepts labeled. Find dy over dx. Take a moment. And this is one thing. This problem is a calculus problem. Calculus is comprised of derivatives and integration. So do not be surprised if you get a problem and you have to do derivatives and integration in the same problem. But we review derivatives. The one thing you don't want to do is just don't mess up when to do what. So find dy dx. Go. What is dy over dx?
Negative 3x squared plus 8x plus 1.
Dy dx means the derivative. Then you're asked to write down the coordinates of the local maximum. You can do that by setting the first derivative equal to 0, solving for x, and then plugging that value in. You can also find the maximum by plugging in the original function and then finding that maximum point. Using this as an opportunity to continue to review some older concepts, okay? This is our function, a little bit skinnier than what we see there, but it is the function. To find the maximum, I can go to second trace. Option 4. When it says left bound, it means you need to go to the left of the maximum point and click enter. Right bound, you move to the right of that maximum point and click enter. Then you click enter one last time for it to guess. And there is your maximum point. That is 2.79. And then 8.21. It is a coordinate, so you want to make sure that you include your parentheses to indicate a point. So the first half of this question was derivatives. The second half is integration because it says to write down the integral representing the area of the shaded region. The integral is that curvy S. What's my lower bound?
2.7.
1.
It's 1.
Oh,
And my upper bound is
4.
4. It is basically those two x values that block off that shaded region. What goes beside the integral?
The function.
The
The
original.
function. The actual function. This one is a write down problem. So it's essentially testing to see, do you understand how to set up the integral to represent that shaded region? And now you actually have to find it. Find the area, not the estimate, the actual area. Do that now. All right, so my area is 15.75. What if it asked you for the exact area? What would you write down?
Fraction?
The fraction form of that. How do you convert 15.75 into a fraction?
15 3/4.
And we will write that as an improper fraction, which would be 63/4. By pressing math 1, okay? Be cautious of the wording. They might try to trip you up and say, find the exact area, because maybe it didn't stop at 0.75. Maybe it was like a continuing decimal or something like that. You want to make sure you provide the fraction answer if it asks you for the exact area. I mean, this one didn't, but like I said, this is review. This is review. A curve y equals f of x has a gradient function of f to the f prime of x equals ax plus 5. The diagram shows part of the curve with x and y intercepts labeled. First off, gradient function. That's a review term or review phrase. What does gradient function mean?
Y-intercept form,
Now, y-intercept form.
Oh, derivative.
slope-intercept.
The word gradient with function means the derivative. So those two words together mean the derivative. So essentially what they're telling you is that you have the derivative, which is ax plus 5. You have to find the equation of the curve. So they want the original function. To find the original function, you need to do what to the derivative?
Find the
The
antiderivative?
integration.
You gotta find the antiderivative through integration. So I'm gonna say the antiderivative of ax plus 5. What's the antiderivative of ax? It's gonna be ax squared over 2, because your exponent here is a 1. So you add 1 to your exponent and then divide by your new exponent. A is just a constant. What's the antiderivative of 5?
5x.
So plus 5x. Here I'm gonna have the plus c because I'm looking for the actual equation. I'm not gonna evaluate it because that's part B, is asking me to find the area underneath the curve. So that's for later. So this is my function. I need to find c and a. To find any variable, whether it's dealing with a calculus problem, a function problem with quadratics, or even exponential, you need to use another point on the function to plug in for x and y to find your missing variables. Unfortunately, we have 2 here. So we're gonna have to plug in 2 points to find my variables. Which one should I plug in first?
Y-intercept.
The y-intercept. That's because that point is at 0, 12. Meaning that if I plug in 0 for x and 12 for y, I'll be able to find my c easily. What is c?
Well,
12. So now I have this function. Now to find a, what would I need to plug in? The x-intercept, which is the point 4, 0. By doing it this way, I'm able to essentially not, not create a system. Find A second, find C first. 4 to the second,
16,
divided by 2.
8,
What's 5 times 4?
20,
What's 20 plus 12?
32.
So subtract 32 from both sides, divide both sides by 8, and A is what?
-4.
So my function, my equation of the curve is -4/2. What's -4/2?
-2.
-2x squared plus 5x plus 12. You can always check this by graphing the function. If you have time, graph the function, see what the y-intercept is, see what the x-intercept is. Now you're asked to find the area underneath the curve from 0 to 4. That's saying the area from 0 to 4 of my function that we just found. This region right here. Find it.